Hello everyone and welcome to video number 2. In this video I shall be discussing how to construct Born-Haber cycles using the processes covered in video number 1. The first example I'm gonna use is for the Born-Haber cycle of sodium chloride. The purpose of these cycles is to determine the lattice enthalpy of ionic solids without actually stepping foot in the lab using the experimentally determined values discussed in video number 1. The first thing you should do to determine or to construct a Born-Haber cycle is to list the formula of your ionic solid as I stated over here, and you would always list it as 1 mole of an ionic compound. According to the lattice enthalpy definition, which is breaking of an ionic solid, thus the arrow would point from the ionic solid towards the gaseous ions, its constituent gaseous ions as displayed over here. The first thing thus to do is to always list your ionic solid and draw the lattice enthalpy arrow and place its constituent ions. These ions should always be balanced with the number of ions in the formula over here. The next arrow you should always draw is the enthalpy change of formation. This definition was covered in previous sections. The enthalpy change of formation is the enthalpy change when 1 mole of a substance, in this case NaCl, is formed from its constituent elements in their standard state under standard conditions. In this example, NaCl would be formed from 1 mole of Na solid, and the moles should be clear: 1 mole of Na solid and half a mole of Cl2 gas, because I only have 1 mole of chloride ions over here. The process, the arrow drawn here represents the exothermic process, which is sorry, this is an endothermic process over here. The endothermic process to break an ionic solid into its constituent gaseous ions, and the enthalpy change of formation of most ionic compounds are exothermic, and thus this value would always be exothermic to form an ionic solid, because the enthalpy changes of formation of covalent compounds could be either exo or endo, but in this case the enthalpy change of formation of ionic solids are usually exothermic. Thus, a quick recap: to construct the cycle, you would first place, this is a cycle without taking into consideration the enthalpy level diagram. The cycles required of you take into account the enthalpy level diagram, which I will show you in a bit or discuss in a bit, but I would like to use this simple cycle first to elaborate on what the cycle is all about. Therefore, a quick recap: the first thing to do to construct the cycle would be to place the ionic solid over here and the gaseous ions that make up the ionic solid over here, and this arrow pointing upward would represent the lattice enthalpy, which is an endothermic process. If this arrow were drawn the other way around, this would be an exothermic process. The second arrow you should draw, or process you should draw, is the enthalpy change of formation of the ionic solid from its elements in their standard states. The cycle is all about now connecting these elements to these ions. Thus, I need to use the processes we learned in the previous videos to convert these elements in their standard states according to their molar ratios, taking into account their molar ratios as well, into gaseous ions. Let's consider sodium solid. The first thing I would do to sodium solid, the metal, would be to atomize it. Thus, the first process would be to atomize 1 mole of sodium solid, and according to the definition of atomization, it's the enthalpy change when 1 mole of gaseous atoms, thus I would produce 1 mole of gaseous Na, and this is 1 mole because I have 1 mole here, from its element in its standard state. Thus this process would represent the delta H atomization of sodium, which is an endothermic process. And once I have gaseous atoms, I can convert them into gaseous ions by ionizing them, according to the definition. And I would only require to ionize sodium once, since it has a +1 charge. And therefore this process here would represent the first ionization energy of sodium. Thus, I've converted sodium solid into a gaseous ion by first converting it into a gaseous atom, which is the definition of enthalpy change of atomization. And once this atom is in the gaseous state, I can ionize it, since the definition of ionization energy requires the atom to be in the gaseous state. The second thing I would do would be to convert the Cl2 or half Cl2 gas over here into a chloride ion. I would start by first atomizing Cl2 into a 1 mole of gaseous atoms. Thus, this would represent 1 mole of gaseous atoms, since I have a half Cl2 here. If this were 1 Cl2, this would produce 2 Cl gaseous atoms. Thus, I would build this cycle according to these balanced formulas over here. The whole cycle should be balanced. Thus, in this step here, as we stated in the previous definition, in the previous video, for the definition of enthalpy change of atomization, which is the energy required to produce 1 mole of gaseous atoms from an element in its standard state, and thus this would represent the enthalpy change of atomization of chlorine, of Cl2 gas. If this were 1 mole over here, and this would produce 2 moles of Cl2 gas, then I would multiply the enthalpy change of atomization by 2, since as we discussed in the previous video. The second step, after we convert the chlorine gaseous element into a chlorine gaseous atoms, the next step would be to convert to add 1 mole of electrons to them, which is the definition of enthalpy change of which is the definition of the first electron affinity, and thus this process would involve the first electron affinity of chlorine to convert it into a Cl-1 gaseous ions from a Cl gaseous atom according to the definition. Now the cycle is now complete. Any missing value I can calculate, but to calculate the lattice enthalpy of NaCl when having all these values is easy, since we would have to move from this side, from this end of the arrow to this end of the arrow through the cycle, and thus we would move through the cycle in this direction. We would move through the cycle in this direction, adding all processes involved. Thus, the delta H lattice in this case would involve adding the enthalpy change of atomization, since we were moving in the same direction, as well as the enthalpy change of atomization of Na, the first ionization energy of Na, as well as the first electron affinity of Cl, because they're all moving in the same direction as we are moving in the cycle. And I would subtract the enthalpy change of formation from the sum of these values, since the enthalpy change of formation is in this direction and I'm moving in the opposite direction in the cycle. Thus, the delta H lattice in this case would equal the sum of delta H all. I'm gonna state all here, meaning I would add all the enthalpy changes in this cycle and subtract the enthalpy change of formation from them, and I can calculate the delta H lattice from this cycle. All the processes in this cycle are endothermic except for 2 processes. The enthalpy change of formation is an exothermic process, as well as the first electron affinity of Cl is an exothermic process. All other processes are endothermic except for the lattice enthalpy, which could be endo in this direction or exo in the opposite direction if they require the arrow in the opposite direction. Thus, to quick recap, to construct a Born-Haber cycle to determine the lattice enthalpy of an ionic solid, I would first place the ionic solid over here and its constituent gaseous ions on top, and draw an arrow to represent the process of the delta H lattice, which is the lattice enthalpy. And then I would draw an arrow towards my ionic solid which represents the enthalpy change of formation of the ionic solid, of 1 mole of the ionic solid from its elements, and then simply convert these elements into gaseous ions using the processes of atomization, enthalpy change of atomization, as well as first and second ionization energy, as well as first and second electron affinities, depending on the charges of the gaseous ions over here. The enthalpy cycle required of us it requires us to take into account the enthalpy change, the process, whether it's endo or exo, and thus has to be drawn using an enthalpy level diagram and not the same as I've drawn over here. I've drawn it simply using a simple cycle without taking into account the enthalpy level diagram, just to simplify the Born-Haber cycle. But the cycle required of us is usually this one over here, which might be a more clear representation of the processes involved. Thus, as you can see here, the enthalpy level is stated clearly. Thus, you should always draw an arrow upwards to represent an increase in enthalpy. And then simply just draw the enthalpy level of your ionic solid at the bottom over here, and thus in this case it's NaCl. The lattice enthalpy drawn upwards is an endothermic process. If it's drawn downwards, it's an exothermic process, and according to the definition, it's breaking. Thus, I would draw it upwards, which is an endothermic process, which is a process which is the enthalpy change when 1 mole of an ionic solid is converted into its gaseous ions, as displayed over here. And thus, this would be an endothermic process, which is a really which has a large enthalpy change, because it requires a lot of energy to break an ionic solid into its constituent gaseous ions. The next step would be to draw the enthalpy change of formation from its elements. Thus, I've stated previously in the previous example that the enthalpy change of formation of ionic solids are always exothermic, and thus this arrow would be pointing downwards. And it's the enthalpy change when 1 mole of an ionic solid is formed from its elements over here. The next step would be to link the cycle by converting these elements in their standard states into these gaseous ions using the processes we've learned in the first video. The first process over here would be to convert the element of sodium solid into gaseous atoms, and this is the definition of atomization. And thus, since it's 1 mole over here, I have 1 mole of an ionic solid, of a metal element, and it's converted into 1 mole of gaseous atoms, and thus the enthalpy change of atomization of Na would be multiplied by 1. If this were 2, which all depends on the formula of the ionic solid, then I would multiply its enthalpy of atomization by 2. The next step, after converting sodium into a gaseous atom, I can ionize it into a gaseous ion, 1 mole. Thus, this is the first ionization energy of Na, which is the process of converting 1 mole of gaseous atoms into 1 mole of gaseous +1 ions by removing 1 mole of electrons, which has to be listed over here. The state symbols in this cycle must always be listed, and if they are not, marks will be deducted. Thus, the first step we did was to convert the Na solid into Na plus gaseous ions, which involves 2 processes: the enthalpy change of atomization of Na, as well as the first ionization energy of Na, which requires the removal of 1 mole of electrons. The next step would be to convert Cl2 into Cl negative ions. The first process would involve the enthalpy change of atomization of Cl2, which is to atomize, which is to produce 1 mole of gaseous chlorine atoms from its element in its standard state, and thus, since we're producing only 1 mole of gaseous atoms, according to the definition, this would be multiplied by 1. If this value over here were 2 moles, the enthalpy change of atomization would be multiplied by 2, as well as its first electron affinity, as I will discuss now. The last process would be to convert the gaseous atom into a -1 gaseous ion, as seen here. And this is the process of first electron affinity of chlorine, which is an exothermic process, and thus the arrow would be pointing downwards. Thus all processes are endothermic, as seen here, except for the enthalpy change of formation and the first electron affinity. If there were a second electron affinity, because this was a -2 charge, the second electron affinity would be an endothermic process, and once again the arrow would be pointing down upwards. Thus the only two arrows that would be pointing downwards are the enthalpy change of formation and the first electron affinity. This is how you would construct the cycle using an enthalpy level diagram to show endothermic and exothermic processes involved in constructing the Born-Haber cycle. Normally we would be given the values for the enthalpy changes, as seen here. I've stated previously that the enthalpy change of atomization are not listed in the data booklet, and thus they will always be given. If we're dealing with a gaseous element here and you're not given the enthalpy change of atomization, its bond enthalpy can be used instead. But if this were a liquid non-metal element, you would be given the enthalpy change of atomization, since these values are not listed in the data booklet. Thus, I have the enthalpy change of atomization of sodium. I have the enthalpy change of atomization of Cl2, which are endothermic processes, as seen here. I have the first ionization energy of Na, which is also an endothermic process. I'm given the first electron affinity of chlorine, which is a negative value since it's an exothermic process, and I'm given the enthalpy change of formation of NaCl, which is also a negative value since the enthalpy change of formation of ionic solids is an exothermic process. And thus, as seen here, I've listed the values for the processes, and I've shown the indirect route that we would take to produce this lattice enthalpy of sodium chloride by constructing a cycle without stepping foot in a lab, and to determine its lattice enthalpy. Thus, to follow this indirect route, as I stated previously, I would be moving with this arrow, with this arrow, with this arrow, and then with this arrow, to move from the ionic solid to its constituent gaseous ions through the cycle to determine the lattice enthalpy. Thus, I'm moving from this side of the arrow to this side of the arrow through the cycle over here. I'm moving with all arrows, and thus I won't be flipping any signs except the sign of the enthalpy change of formation, as stated previously, since I would be moving against this arrow in this direction, rendering this enthalpy change as endothermic instead of exothermic. And therefore, to determine the lattice enthalpy of NaCl, I would add or sum all the enthalpy changes of all these processes listed over here and subtract this process from their sum to produce the lattice enthalpy, as displayed below over here. This is what was done. Thus, the sum, I've added the sum of 109, 494, 121, and -364 for the enthalpy change of for the electron affinity of chlorine, and I subtracted -411 from their sum, thus rendering this an endothermic process to produce positive 771 kilojoule per mole for the enthalpy change or the lattice enthalpy of sodium chloride. This was fairly a simple example. I've also listed here as a quick reminder that to determine the lattice enthalpy of compounds using Born-Haber cycle, you would sum up the lattice enthalpies of all processes involved and subtract the enthalpy change of formation from that sum, because we would move against the arrow over here in all cycles. This applies to all Born-Haber cycles. This was a fairly simple example since the molar ratios involved were all 1-to-1 ratios, since the compound has 1 mole of sodium ions and 1 mole of chloride ions, as seen over here. I would like to cover a different example to simply construct a cycle that involves different molar ratios. I'm going to start using the example of magnesium chloride. I've once again listed the simple cycle over here that doesn't take into account the enthalpy level diagram. Thus, the first thing I did was place 1 mole of the magnesium chloride solid over here, and I've listed its constituent gaseous ions. I have 1 mole of Mg2 plus gaseous ions and 2 moles of chloride -1 gaseous ions. And the next step I did was to list its enthalpy change of formation process in this direction over here, which is the enthalpy change when 1 mole of this ionic solid is formed from its constituent gaseous from its constituent elements in their standard state under standard conditions. Thus, the element of magnesium is Mg solid, and I have 1 mole here since I have 1 mole of magnesium in the formula, and I have 2 chloride ions over here, and the element that makes up Cl is Cl2 gas, and thus I wouldn't multiply it by half since I already have 2 chloride atoms in this molecule, since I require 2 in this formula. The next step would be to link these gaseous ions with these elements as stated previously. Thus, I would first convert the magnesium solid into gaseous ions, and since I have 1 mole over here, then this would be 1 mole as well. And thus the enthalpy change of atomization of magnesium would be multiplied by 1. The next step would be to ionize magnesium. But Mg has a 2 plus charge, thus this process would involve its first ionization energy to form the +1 ion and its second ionization energy to convert the gaseous atom into a gaseous +2 ion as shown over here. The next step I would do would be to atomize the Cl2 gas, and once I atomize Cl2 gas, it would form 2 chlorine gaseous atoms. And thus, since the definition of atomization is to produce 1 mole of gaseous atoms from its elements in their standard state, I have formed 2 moles over here, and thus the enthalpy change of atomization would need to be multiplied by 2. The next step would be to convert these 2 moles of gaseous atoms into 2 moles of chlorine -1 gaseous ions. The definition of first electron affinity is the enthalpy change when 1 mole of electrons is added to 1 mole of gaseous atoms, and in this case we're adding 2 moles of electrons to 2 moles of gaseous atoms. Thus the enthalpy change of the electron affinity, the first electron affinity of chlorine, would need to be multiplied by 2 because this is per mole of gaseous atoms, but I have 2 moles of chlorine gas over here. Once the cycle is formed, I can calculate the lattice enthalpy for magnesium chloride by simply summing up these processes over here. The enthalpy change of atomization of magnesium and chlorine multiplied by 2, the first and second ionization of magnesium, as well as the first electron affinity of chlorine multiplied by 2, and subtract the enthalpy change of formation from the sum, since we would move through the cycle in this direction, and we would move against the enthalpy change of formation. I've taken a snapshot of the book as well to show you how this should be drawn using an enthalpy level diagram. As you can see here, as stated previously, I would start by placing at the bottom the enthalpy level of magnesium chloride, theoretically speaking, of course, magnesium chloride solid. I would draw the first arrow would be its lattice enthalpy, which is to convert 1 mole of magnesium chloride into its constituent gaseous ions, which in this case are magnesium 2 plus in the gaseous state plus 2 moles of chloride -1 ions in the gaseous state. And this process would be an endothermic process. The second enthalpy level I would draw would be that for the enthalpy change of formation process, which is when 1 mole of magnesium chloride solid is formed from its constituent elements in their standard states under standard conditions. And in this case, this would be 1 mole of magnesium solid and 1 mole of Cl2 gas, since this would produce 2 chloride ions which are present in the formula of your ionic solid. The first step would be to atomize magnesium solid into magnesium gaseous atoms. And since I have 1 mole here, then this would be multiplied by 1. The next step would be to ionize magnesium, the first ionization energy of magnesium, and since it's 1 mole, I would multiply its first ionization energy by 1, and I produce 1 mole of electrons by ionizing it. Thus, the first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to produce 1 mole of gaseous plus 1 ions, as seen here. The next step would be the second ionization energy. I would remove an extra mole or another mole of electrons from this magnesium plus 1 ion to form magnesium 2 plus ions, and since it's 1 mole here, this would also be 1 mole. But now I would have 2 moles of electrons in total, since these 2 moles of electrons are removed by the processes of the first and second ionization energies of magnesium, and then these 2 electrons will be transferred to 2 moles of chloride ions to form these gaseous atoms. The next step would be to atomize Cl2 gas, and thus to produce the definition of atomization once again is the enthalpy change when 1 mole of gaseous atoms is formed from an element in its standard state under standard conditions. In this case, we are forming 2 moles of gaseous atoms, and thus the enthalpy change of atomization of Cl2 would be multiplied by 2. This process is endothermic. All these processes are endothermic. The final process, which is the first electron affinity of chlorine, is an exothermic process, and thus the arrow would be pointing downwards as discussed previously. And thus the first electron affinity definition is the enthalpy change when 1 mole of electrons is added to 1 mole of gaseous atoms. But in this case, we're adding 2 moles of electrons to 2 moles of gaseous atoms to form 2 moles of negative 1 ions. Thus, the enthalpy change, or the first electron affinity of chlorine, would need to be multiplied by 2. And now that the cycle is linked, to calculate the lattice enthalpy over here, one would move through the indirect route through the cycle, which is in this direction as stated previously. And thus I would sum up the value of all these processes, the enthalpy changes of atomization, the first of magnesium, the first ionization energy of magnesium, the second ionization energy of magnesium, and the enthalpy change of atomization of chlorine multiplied by 2, plus the first electron affinity of chlorine multiplied by 2, and then I would subtract the enthalpy change of formation from the sum of these processes, since I would be moving against this arrow when taking the indirect route through the cycle to calculate the lattice enthalpy. If this arrow were drawn in the opposite direction, I would still calculate it the exact same way, but will flip the sign of the value once calculated. Therefore, if this process would be an endothermic process in this direction, but if the arrow was drawn in the opposite direction, I would still sum up all these values and subtract the enthalpy change of formation from it, and simply flip the sign of the value produced once calculated using the indirect route over here to produce an exothermic process if the arrow was drawn in the opposite direction in the cycle. So care should be taken. You should always look at the arrow of the lattice enthalpy in your cycle. If you were given a cycle that has already been drawn, always check the lattice enthalpy if it's pointing upwards or downwards to determine the sign of your lattice enthalpy change. I didn't put the calculation for this. You simply plug in the values for these processes and add them as discussed previously. I've displayed over here, I've also displayed the values of the lattice enthalpies listed in the data booklet. They are listed in table 18 of the data booklet. As you can see here, you're given the alkali metal halide lattice enthalpies, alkali metals with any of the halogens over here, and they are all positive endothermic processes according to the definition. If you require the lattice enthalpy of formation, which is an exothermic process, you would simply flip the sign of these values. And for other substances from group 2 or transition metals as well, ionic solids have been listed in the table below. Sometimes you will be given questions in which the lattice enthalpy is given, but one of the processes is missing. For example, if I were given this question and I'm given all the values, the lattice enthalpy, as well as all these processes except the first electron affinity of chlorine, I would calculate it the exact same way. I would put the lattice enthalpy value equals the sum of all these processes, and placing this process as x, or 2x in this case, and subtract the enthalpy change of formation from these values and solve for x. Thus, you can always construct the cycle the same way, and for any process that is missing and you're required to calculate, you can simply place it as x. I have attached a worksheet which I require you to solve and send by midnight tonight, but it also requires knowledge of video number 3, so please proceed to video number 3, which covers the comparing lattice enthalpies of different ionic compounds. What factors affect the lattice enthalpy of different ionic compounds, which are basically the same as the factors that would affect the strength of an ionic compound that we covered in topic 4. Please proceed to watch video number 3, and thank you for watching.